Good evening. It's a great pleasure to have here Professor Alex Kalamkarov. It's in the last 3 years he has been at CEFET and UFRJ giving some lectures, developed some research. Professor Alex Kalamkarov is a specialist in micromechanics of materials, has a lot of publication, books, have an extensive curriculum. So you can see the curriculum at the site of Halifax. He's a professor of the Mechanical Engineering Department of Dalhousie University in Halifax, Canada. So it's a great pleasure to have you here in CEFET. He will give a lecture in composite materials. Professor Kalamkarov has participated as a visiting professor at CEFET and UFRJ in a 2 years CNPq Science Without Borders research project, developing research and presenting lectures and short courses for several Brazilian research groups. I'd like to thank Professor Alex Kalamkarov. Thank you very much.
Thank you, Professor Pacheco. Thank you for coming, and I'm very glad to see you, and many young faces, many little older faces of my friends, colleagues. I'm blessed with my friendship with Brazilian colleagues that lasts for quite a while now, maybe 10, 15 years. And we had interesting collaboration supported by grants of different caliber, including last one for 3 years, which was within Science Without Borders program. I visited 3 times CEFET and Federal University of Rio de Janeiro with Professor Marcelo Savi heading there and Professor Pacheco here. And we hope to get more support in the future. Today I will talk not really about micromechanical modeling, which is very analytical, mathematically saturated topic, but rather it will be educational lecture about what are the composite materials, what are smart structures, a little bit about nano-composites. So this lecture is more addressed to younger generation of students or colleagues who are not really much in composites, although maybe for people who work in composites that will give also some, that's a little premature. I have here also some videos to show, but not yet. All right, so let's start. So what we will do is I will tell you what are the composite materials, the types of composite materials, how they are manufactured. I hope to show you videos which already started prematurely. Where composites are used, what are small structures, what are nano-composites and carbon nanotubes. First of all, what are the composite materials? Composite word is the composition. So basically this is the composition of a binding material, which may be like a resin, most probably polymer, and different kind of inclusions, which may be fibers or particles, which make the composite. So they are made by combining 2 or more natural or artificial materials in order to maximize their useful properties, minimize their weaknesses. And of course they are advanced materials, but yet analysis shows that they are actually the oldest materials human used in the history. And I will show you several examples. Well, starting from the ancient material which was used like a brick here. So it's a mixture of mud, straw, sand, and rocks. So that is one of the oldest structural material used in different countries, of course in Egypt, and actually in Mesopotamia as well, as a long time ago, as 3,000-4,000 years ago. Before that, papyrus was used as a material for writing, And as a matter of fact, it's a laminated material. I will give the strict definitions of all these words for those who are not familiar a little bit later. So this is kind of a papyrus from which the plant from which the papyrus is made. And this is the Mongolian bow, which actually Mongolians invented the composite bow because that thing was made from combination of 3 or 4 different materials. So very effective one. Now, interestingly enough, I spent some time in Italy last spring, and I was at the University of Bologna talking to different people, including philosophers and historians of religion. They told me, check the Bible. What about this Noah's Ark? As a matter of fact, what Bible says that the Noah's Ark was built out of gopher wood, covered inside and out with pitch. Now, this is wood, and the pitch is basically viscoelastic polymer, natural viscoelastic polymer. So basically, the Noah's Ark, if it was built, it can be called a composite structure. Moreover, interesting thing about Tower of Babel. As a matter of fact, what Bible says is literally the following. Come, let us make bricks and burn them thoroughly. And they used brick for stone, and they used tar for mortar. So basically, it was not like a stone structure, if it was ever, but it was actually composite structure made of different bricks made of composites plus the tar. So pretty much a modern type of composite structure. All right, so let's get now to our nowadays advanced composite materials. So today, let's start with classification. What types of composite materials exist? The first type is called laminated or laminar composites. This composite material consists of 2 or more layers of different materials that are bonded together, right? So that makes a laminar composite. Another type, fiber reinforced composite. This is material which is with chopped or continuous fibers embedded or bonded by a binder material, which normally we call matrix. So matrix bonds fibers or chopped or long fibers. The third type is particulate composite. This is, again, the binder material with embedded particles. The shape of particles can be pretty different. They can be randomly distributed or regularly. So to summarize, any kind of composite material, generally speaking, will belong to one of these three classes. Apart of that, there are tons of different thin-walled composite structures, which I want to put like a separate, because as a matter of fact, they can belong to each of these 3 parts. They can be laminated, they can be fiber reinforced, they can be particulate. The thing is that they are thin. So the thickness is much smaller than the tangential dimensions. This is a great advantage because they are light, they are strong in certain directions which are needed for this kind of particular design, and they are cost effective. So you see different examples, and we will discuss many particular cases a little later. All right, so let's now step-by-step check, starting with laminates. As I just told you, so these are the layers bonded together of 2 or more other materials with adhesive. So you can see these layers. You see the fibers, they can have different directions. This kind of laminate is called cross-ply. There are some mechanical models which allow to calculate overall mechanical properties of these laminates without big difficulty, and they are pretty practical. They are used almost everywhere in our modern society, starting with aircrafts, and that we will talk separately in more details. They are used in cars, in boats, in bikes, and even in some kind of armor protection. As a matter of fact, the most effective protection, bulletproof vests, are definitely made of specific kind of laminates, and they are designed specifically to stop bullet of penetrating. So it penetrates one lamina, then another, and maybe it's stopped somewhere in the between. Of course, the fibers which are used are very specific, very strong, and it's a big research going on there. Similar thing with windshields. Windshield, which any car has, a good windshield is a really good laminate, which again has a lot of protection through the breakage, especially through the bullet penetration in case of military cars. Now, not all applications of composites are high-tech, I would say. As a matter of fact, if to count the monies which are invested in composites for different applications, I will not be surprised, I don't have that statistics, but I will not be surprised to find that such kind of household applications as you see here may have a bigger market for those materials rather than some very high-tech, maybe more expensive, but much smaller volume products applied. Indeed, this is actually called a laminate, right? You know, the floors, the decorations, the shingles. They are actually exactly what the laminated composite is. Keep that in mind. Now let's get to fiber reinforced materials. So again, you have here the picture, and then you have the micrograph. What fibers can be used to create fiber reinforced material? As a matter of fact, many laminates are made of layers. Each of layer is a fiber reinforced material. It's pretty typical, not always, but very typical. So what fibers? Well, the most typical fiber is the glass. So these are the glass fiber, the mandrel with the glass fiber, and then the material will be called GFRP, glass fiber reinforced polymer. This is the carbon fiber, it's black color, and CFRP stands for carbon fiber reinforced polymer. So the glass fiber is cheaper than carbon, but carbon has some superior properties for certain applications. Now, being in Brazil, it's especially important to mention that a lot of fibers are actually, or can be, or are actually made from the natural materials. And I know that in many Brazilian universities there are special teams which do work about developing natural fibers and making composites made of natural fibers. The most used plant fibers are cotton, flax, hemp, aloe, jute, bamboo, banana, coconut, and acai, which is particularly, Brazilian product, creates fibers which are successfully used in composites. Now, this is interesting thing because these fibers are made from basalt. So basically, it's like a kind of a rock. Well, apparently, the car can be built by material which is based on basalt fibers. This particular beam looks like it has a plant fibers. I don't know exactly what kind of plant, but according to that color, well, maybe banana fibers. So that's what is very interesting and cost-effective, and for certain applications, pretty much what you need. Now, let's get to how to manufacture all these goodies. So how to make those materials. And here are the most typical, the most important methods of processing or manufacturing of composite materials. Number one, hand-lay-up technique. I will show you videos, you will see details, but speaking shortly, it's a very simple technology. If you want to make certain shape, you make that, shape of plastic or maybe plywood or wood, then you put protective layer, and then you start putting fibers or fabrics of fibers, then you put resin, you kind of, press that, even like that, very easily, and then you put it in some kind of oven, autoclave, heat it up to certain temperature so that the resin solidifies. And then you take it out, clean it up, and your part is made. So that is probably the most primitive but extremely widely distributed method, because it allows you to create different shapes without, let's say, high-end technologies. Pretty simple thing. In your lab you can do it. Now, resin infusion is more or less similar idea, except that the resin is infused in what is called vacuum bags, which take certain shape, and it's more technological and used for more higher technological parts. You will see example of that as well. Now, two automated methods are the most typical. One is called filament winding, when the fibers are wound on the mandrel, wet in the resin, then solidified, you get the part. Well, evidently, what kind of shape you will get? Well, axisymmetrical. So if you want to make axisymmetrical part, filament winding is a very good technology. And finally, what I want to show you is the pultrusion. Pultrusion is when you actually pull the fibers wet in resin through the pultrusion die, heat it to a certain temperature, when solidifies the resin, and you can get any kind of profile of material coming out there. Not necessarily axisymmetrical, as a matter of fact, any kind of prismatic body. Well, let us look how it works. So let us start with this manual layup. So as you see, it can be very large volume operation. An autoclave can be really huge. So basically imagine that you put here, well, you can put the whole fuselage of airplane. That's probably the reason why of this size. Or you can put the pressure vessel designed, for example, for maybe even nuclear plant or something like that, or jet engine. Jet engine cannot be that big, of course. All right. Now, there are different kind of technologies which allow you to make the fabric placement in a very specific way to optimize the strength of that fabric in certain directions. Well, according to that black color, the fibers are here carbon. And here you can put the tape laying, so you make that material that you can later use for example, for hand layup with the resin, and after solidification, you will get a very good quality composite part. Now, let us start with the filament winding. And as I promised, I will show you some educational movies here. Hopefully, technology will be friendly. So this one doesn't speak and doesn't play music, but it has comments here. So here are the fibers. Here is the resin bath. So you will see in a minute how the fibers are impregnated in resin, because they run through that resin. And resin is very liquid here. Now, some more interesting technology will allow you to place fibers not just straight and stupid, but also to make certain pattern which you want to have right here. And then that mandrel rotates, as you see here, and the machine moves. Regulating the relative motion, the speed of how that machine moves, and the angular velocity of the mandrel, you can actually regulate the angle at which the fibers are wound on that mandrel. So basically, you are making a material extremely strong, because you can make the optimally designed distribution of angles at which the fibers are wound on that mandrel. Well, then you put that, well, in this particular example, you had a heated mandrel, and then you put it also in that infrared lamp. Well, for certain kind of polymeric resin, that's the way how you cure the resin. So after that operation, the resin becomes, also you put in the oven, as you see, to cure. And then you keep that at certain temperature during the certain time. And then basically, the technology comes to the conclusion. And what is beautiful about that? what you get as a result is the part which is ready, completed. You don't need to do anything more, but take it out, pack it, and ship to the place which needs it to put it in certain kind of device or structure. Well, that was a good example. Now, another one. That has a music, and it's funny. It is very informative. They give you lots of details, but it's a little long. We'll see how we can sustain that if we want to see all of it, or I will cut it somewhere there. That worker must know what he is doing. It's not that difficult, right? And here we go. Well, pay attention that this machine makes not just a pipe-like cylinder, but actually the pressure vessel with caps. So it's completely surrounded by this filament-wound composite material. So basically the final product will be ready in a couple of, well, maybe half an hour, well, plus curing process, right? Now it changed the angle actually very much. Now that's interesting. Then it puts the hoop strengthening there. So I mean that pressure vessel they are making will be top technologically strong. As you see, they are also using the best quality carbon fibers. It's a very detailed video. Now I want you to show one thing that will make you happy, because it is Brazilian technology. Here are glass fibers, evidently, but look at the size of this mandrel. It's probably huge pressure vessel or tank, maybe for oil or something like that. Now here they actually prepare the mandrel. Put the liner. I want to show you when it starts winding process. It's almost there. Yeah. So as you see, it's a wet resin, shines in light. So you can make wall as thick as you like. You can make it half a meter thick. As much as you want, you can wind it. So the strength can be enormous, of course. Let us cut it. Yeah. Oh, here we are. All right, now let's go forward. I think it was enough of winding, right? The next I want to show you is the pultrusion. So this is the schematic of a pultrusion machine. So here you have the rack of mandrels with fibers. Then you have the distribution fiber feed system, the resin bath, the distributor where you want to put the fibers in certain locations. Then that die. Die is the massively built of steel device which has normally two parts, lower and upper. You close it up, and it gives you the cylindrical profile of the part that you want to make. Now, everything that is pulled by different type of pullers. You will see videos with different types of pullers. And here, after the die, actually the material is cured. So normally it doesn't need any further curing if you did that pultrusion. And let me show you now how it looks in real life. So this first video is really showing all the steps that I just said. The fiber yarns are pulled through the resin bath, wetting the fibers, so the fibers are wetted. So this first part reminds you very much about the filament winding, right? And then look how the fibers are also placed at certain angles and in certain shape. In this particular situation, they are making a pipe. So they put the fibers in the kind of a round shaped woven material. Then it will be solidified with the resin, and result you will see very soon. So this is the pultrusion die. Now look, it shows you how the resin is heated and quickly cured. So here is the physical chemical process of curing the resin. And then that guy here, the structure is already done. It's made. So now this way of pulling is called caterpillar. A caterpillar, basically it means that you rotate that and it, with friction, it pulls the part forward, right? And then the cut-off saw, you can just measure how long detail you want to make. You can make it extremely long if you need. Well, also you need to think about transportation. And then you cut them, you put them together and ship. Now you will see a different process, little bit. Pultrusion is the same, but you will see a different type of pulling mechanism. So these are fiberglass drawings. And you have also fiberglass mat here. So you will see why. So as you see, the feeding is quite complicated. And this is a different type of pulling mechanism. It's like a stepwise. You pull it, as you will see now. So it's not a caterpillar, right? So this is the guide. Fibers are impregnated with resin. You see here, you don't have a resin bath, but rather some kind of container in which the resin is supplied under the pressure, and it impregnates all this combination. Pulled out. And you can make any kind of profile of this structure. Here is the cut-off saw. Now it will show you how the process is going. Another interesting thing I found, it's a different one, and last one about pultrusion. Quite different. Look here. Instead of fibers, they use some kind of already woven fabric. In my opinion, it's made of glass fibers. It looks white, and these particular fibers look like glass fibers. But look what they are putting inside of your die. Not singular fibers, but that kind of, let's say, mat of already woven fabrics, and pretty thick. And resin is impregnated somewhere here. So basically that's the resin, right? Under the pressure, it gets all through the material. And then as you see, these are the heating devices. So you have 3 zones of temperature. And then the result coming out. Well, this is a high-performance composite beam is coming out, right? And as a matter of fact, here, it is already finished. That's the final product. You cut it somewhere here, and then you put it and ship it to maybe construction site or wherever you use it. Now, of course, it is a solid rectangular shape. There is also the device which is pulling that thing. And as you see, it is pretty bulky because in that particular case, the pulling force must be pretty high, considerable pulling force. Much higher than in case of, that first example of round pipe made of several fibers. So therefore, as you see, that mechanism is really bulky and very strong. And here it comes, the product. All right. So we got the pultrusion. We already did that. Now I want to show you, well, maybe 2 examples more. This is about hand layup. You remember I said that I will give you more details. I know that some of you want to make some airplanes, right, or boats or something. Well, how you will make the part, which you may wish to make a composite, I will show you in that first example. How to make fiberglass boat.
Works. They're sleek, they're fast, and they're fun. Fiberglass boats can jump waves and turn on a dime. The fiberglass body is low maintenance and durable, so these watercraft don't deteriorate the way wooden boats can. A computerized saw cuts out the wood pieces they'll use to build the mold for the fiberglass boat. It takes a team of artisans about 15 months to design and build the mold. They first construct the frame. Then they build up the shape out of fiberglass. The mold must be perfect in order to cast a boat that's free of faults and defects, so they painstakingly work on the mold's finish in particular, coating it in a special high-resistance paint that will withstand about 8 years of castings. Once they've finished the mold, they can begin casting the fiberglass boat. The equipment feeds just the right ratio of fiberglass to plastic resin. Fiberglass is glass in the form of very fine, flexible fibers. They may look fragile, but those fibers are stronger than steel, and they won't burn, stretch, or rot, so they make perfect boat-building material. Workers make sure they roll the fiberglass into every nook and cranny. This is critical, because if they don't apply the fiberglass thoroughly, the boat will have structural defects. As heat within the fiberglass builds up, it hardens. Next, they roll on a material called roving. It reinforces the fiberglass and makes it more rigid. They also install wood at the spots where they'll later mount equipment. They coat the wood with fiberglass to protect it from moisture. After about an hour, it's time to extract the casting from the mold. They use a lever system to lift out the hull. They cut out holes for the mechanics. Then they install the boat's deck. They install the motor and the electrical wiring for the mechanics and plumbing. The boat truly takes shape in the final assembly. They put together the upper part of the boat, called the shell, and the inside, called the liner. They install the furniture, then certain components by hand, such as the dashboard.
Well, and they sell it for 2 million reais, right? So basically, you can do it at home, right? I mean, in terms of technology, there's nothing that you cannot do yourself. Well, size, of course, and scale can be different, but the idea, that's what I mentioned, that the hand layup is the most easy to implement for any particular applications. You are not very tired. I have one more video. You want to see it? It is a little long, so I will be cutting it off because I think it's like, you know, too many details, but it is about resin infusion. And by itself, it is an interesting thing. Let's see. I think it's the last one I prepared. And they are actually making a blade, you will see, for a wind turbine. You see that drawing here. They are making this blade. It's huge. I think it's from here to that far corner, at least, the size. And of course, this is more responsible structure in terms of quality. That's why they will use that particular, no, I thought it is longer. Well, 3 meters, okay. So this is just a profile. It is not the product. That's a plastic profile. And it's a kind of, you know, labor-intensive thing in terms of how many steps they use to put that vacuum bag. But if you look at that video, you will agree with me that this can be done also with a little training and instructions. You don't need to be highly qualified, just need to be, you know, accurate. So they put that thing which will keep it in vacuum. You will see vacuum channel allows air to flow. Yeah, that's interesting. Resin runner. So you have somehow to supply the resin inside, right? Look what they're doing. So it's just a flexible cord they insert in that protector, and then they glue it. Double-sided tape, so not a high technology, you know, just to tape that thing in. That is the dispensing machine of a silicon, so they put the silicon around. To ensure proper seal, because you need to have a vacuum there. Then you spray the rubber. The resin runner. It's pretty much the same thing they're doing. Of course, they cure the resin. Now they will start making the part. Yeah, here they are putting that back. So remember, they made it especially for that. Okay. Ship. So the resin flows in that vacuum bag from that primitive pot full of resin. When it is full, they stop it. I'll remove the bag. All right, so that's done. Okay, I showed you actually the details on this manufacturing. Now let's get back to presentation with slides. So where the composites are used. First of all, composites started to be used in military, especially in aerospace applications, by two reasons. Number one, they had money for that. It was very expensive. And number two, it was extremely high technological, so they needed the best materials. Now, this is a fantastic machine, of course, a military plane, a Lockheed Blackbird. Well, as a matter of fact, it was done in 1966 and worked till 1999. So it's a very early example. If you look, the titanium was 85%, while the polymer composites were 15%. For that time, it was quite a record. Now, if you compare Boeing 777 and later on Boeing 787, you can see that here you had 11% of composites. Here you have 50% of composites, right? You can have also the amount of carbon fibers used in Dreamliner Boeing 787. So you see the progress about 9 years. The composites are like 4 times, over 4, maybe 5 times increased. Now I have a very interesting diagram a little later to show you, but also the helicopter blades, it's something that people don't realize, that Boeing, for example, used 1,500 composite parts to replace 11,000 metal components in the helicopter. Now this is an interesting diagram. That plot shows you the military aircraft percentage of composite by weight. This one shows the airliner. So this is the civil aviation. This is the military. And you can see the airplanes with the history. So as you see, the last one, Eurofighter, has 50% of composites by weight, right? Now, if you look, the blue color is the Boeing. The beige color is the Airbus. So here the Boeing 787 has 50%. Now Airbus, the last edition, whatever it is, number here 350X something, it has even a little more than 50%. So basically you can see that the trend in military and civil aviation is very, very similar, except that here the explosion is even more profound. So you can say that by weight, modern last edition of airplanes have almost 50% of composites. Now, of course, the Navy ships are made of composites here, the bridges, prostheses, and the sporting goods. This is a general kind of slide. I will show you more details. Infrastructure. Now, you saw this thing, how to make this blade. You saw how to make these are pultruded composite parts, all of them. So as you see, you can make different profiles, you can make different materials, of course, different strengths, and all of them are technologically made using the pultrusion. So this is huge market. I think that's the biggest market in the world in which the composites will be used, and already. Now, interesting that not only frame of bicycle made of composites, but, which I didn't know, the wheels. So you can see that this is the carbon fiber filament wound wheel. Now, another example that I also didn't know before I started preparing that, Comanche, high performance yacht. Look at this sails. Normally we think that sails are made of fabric, right? Now look here. So composite sail, 3DL technology. So the mold, base film, 3DL yarn structure. So this is made of composite fibers, some kind of screen and top film. And now you will see what it makes. How it is done. 3DL, this is the company in the United States which makes this kind of sails. Look here. So they put all of that, hand they up, huge size, carbon fibers, the shape, optimally designed, the shape of the sail, which is solid, by the way. And then this poor guy is hanging over that sail with the heating element, so he cures the resin, right? Excellent job. Then here is the final product. Well, I really didn't know about that, but apparently these sails are the top notch, and of course they are used for this, special kind of yachts which make championships. Well, of course, if you have money, you can purchase it for your yacht as well. Now, some other examples, sandwich structures. Well, low density core, high density facing sheets. That's the secret of the sandwich structure. When your core is white, that extremely enhances the bending stiffnesses, not much increasing the weight and cost of the structure. So that's the secret why these guys are used, especially in aerospace and in marine engineering as well. Well, now here I gave you different examples of this core, which is made of different materials, starting even from aluminum, and they have different features like low cost for aluminum, thinnest insulation for fiberglass. Aramid is fire resistant, so if your structure is facing elevated temperatures or fire, then you use aramid. And polyurethane for cushioning, and also it is not afraid of moisture. So depending on application, you can use different materials. Where are used? Well, in aviation, as I mentioned, in any kind of transportation, in modern high-speed trains, in boat industry, in construction, and this is an interesting example. Actually, this sandwich, as you see, honeycomb core, is made of a cardboard, basically pressed paper. And then it is, of course, encapsulated in thin polymeric upper and lower layers, so to prevent water coming in. But it is extremely light, and apparently, as you see here, they can surf the waves. I'm not sure it is as strong as high-performance surfboards, but it's very interesting design too. Biomedical applications gain, so different parts, or like sockets or food, or even specially designed blades for these Olympic runners, and maybe some not Olympic champions, but just people who are unfortunate having no legs can use them to run. And these are the applications. Of course, the downside of the composites is that they are vulnerable to breakage, delamination, break of fibers. So basically, since the fracture happens mostly inside of these materials, to some extent you are not able to see them much in advance, to fix them. There are some technologies, but basically what is the best thing is to have structural health monitoring. So basically to input inside, to insert some kind of sensors which will monitor the, what we say, health, which means, for example, the strain state of the structure. So if the strains are normal, it's okay. If you see that certain places are strain and therefore stress concentrators, that means that some defects are there. So then you can take measures. So that brings us to the topic on smart materials. So what are smart materials? Materials that have sensors, actuators, and control. So that you have the most difficult and the most comprehensive, let's say, intelligent structure. If they don't have control, then it can be passive smart structure. It may not have actuators, only sensors. Then it is a health monitoring, right? But the most comprehensive when you have all of them. And there are many examples of that. And of course, we want to follow the idea of living beings, not necessarily humans, which do have all these components in their bodies. There are several types of actuators plus sensors materials. I just, give you introduction. So I am talking about piezoelectric, shape memory alloys. Piezoelectrics, they of course react on electric potential, vice versa. Shape memory alloy reacts on the heat, changing the shape. Here is a little more detail. So you apply electric voltage, you change the shape, so you see the deformation. Or you apply force, you generate the electricity, so two-way process. This one you can use as a sensor. This one you can use as an actuator, right? So applications, the original loudspeakers still is used. Smart structures, maybe number 1 versus 2 with this shape memory alloy, the most typical actuators. For example, I personally solved that optimization problem that if you put a good piezoelectric actuator in the bottom of that cantilevered beam, you can reduce maximum deflection by 28 times. So I don't give here mathematical justification, just the result. Shape memory alloys, and you have one of several world leaders in shape memory alloys here in that room. So I will not, talk about that more than I need. But for the students, basically what it does, the original shape, then you can deform it, then you heat it, it gets to the original shape. So the heating, which can may be made by electric field as well, right? Changes the shape, therefore it is the actuator. So where it's used, smart structures, vibration control, in biomedical applications like blood clot filters, and also in eyeglass frames, although I don't think it's very successful. I think they decided to refuse of that by some reason. Anyways, here are several examples that I found to show you different applications. Like for example, this is a Tokyo installation, 300-ton pendulums here, which damp the energy of earthquake by 35 to 65%. Well, which means that this skyscraper can survive. If there will be this control, it will of course be demolished. In this particular application, I personally was used. We did a work on embedding fiber optic sensors inside of FRP reinforcements, which would be put in the bridges, so that sensors are inside of this FRP reinforcement in the concrete. They signal strains, which goes to the headquarters, to the monitoring station, and in case of something goes wrong, the team goes immediately to that bridge and takes care. So this kind of overall system is still on go, but it is already very much based on certain achievements that are already in place. Here are actuators which can fix the vibration and damp the vibration, and also move probably the frame of that spaceship antenna. The idea is shown here basically. So it's a frame-like structure. You have certain most probably piezoelectric actuators, which work both, like sensors and actuators. And here are, this my old example, I found a new one. Actually, interesting thing, bi-morph actuators, they are made of at least two different, most probably piezoelectric materials, which effectively can change the shape. So basically, by controlling those bi-morph actuators, you can control the shape of the wing. Here, the distribution of piezoelectrical actuators can damp or suppress wing vibration. Well, by making wing much more, functionable. This is another example which I maybe already showed you before. This is about the stabilizing the image of cameras, or even smartphones now have that device, which actually moves the CCD, which is the sensor that captures image, to actually eliminate the vibration or the shaking of your hand. So it's a very now widespread technology. Almost every kind of camera and smartphone has it. Now, K2 is the name of company which produces smart skis. So they integrate piezoelectric actuators inside of the ski, which actually senses the undesired bending of that ski and puts it back by actuating through the closed loop control system. And one more example, also we discussed that a little earlier, electroactive polymers. The research is going on. So these are type of polymers which act to some extent as piezoelectric materials. The difference is that these polymers have much higher rate of strain. So investigation shows that it is in the range of how the real muscle works. So it's more and more getting to not only in robotics as artificial hands, but also to put the muscles in the biomedical applications. Now, couple of words about fiber optic sensors that I mentioned before. Actually, this is done in my lab. The fiber optic, the optical fiber is embedded in the pultruded composite. These are the glass fibers, sorry, and this is the optical fiber. So you see the relative size of 500 times magnification. And two types of fiber optic sensors we used, Fabry-Perot. Basically, it's mechanical when that changes distance because of strain. The signal which comes of a light through the fiber optic can be monitored to measure that strain. And this is the Bragg rating. Here you don't have any cut. You have so kind of, defects actually you impose in the fiber, in the optical fiber. And then when the local strain happens, the frequency of light which is reflected gives you the measure of that local strain. So we basically embedded that thing, the optical fiber, inside of pultruded die when we made these FRP reinforcements. Multi-wall can be made in different ways, how it is here. Actually, that shows the technology, physical process of making carbon nanotube. And here it is why it is of interest. Carbon nanotube is 375 times stronger than steel, and it is 5 times stiffer than steel. So embedding those carbon nanotubes into the composite makes that composite nano-composite, plus increases certain properties of that material. And there are interesting ways how to do that. Well, that will be beyond of my today's presentation. And of course, they have superior strength and stiffness properties. Well, to finalize, with respect to monies, it is of course relative, but it says that by 2017, it will be $35 billion, the market of composites. I think it is really underestimates it because it's impossible to count all, budgets for all composites used. But nano-composites are extremely quickly developing, so 24% great growth rate from 2014 till 19. And of course, just to summarize, to remind you what we did, we learned about advanced composites, methods of manufacturing, use. We spoke a little bit about smart structures and nano-composites. Well, and that finishes. Thank you so much for your attention. What composites?
The nano-composites.
Nano-composites.
Yeah.
Well, I don't know where you can see it. Applications are absolutely identical to any other. The thing is that if you have, let's say, fiber reinforced composite material, and you add to those fibers, let's say, a perpendicular set of carbon nanotubes, that extremely increases the bonding between fiber and the matrix. For example, that technology is in place. Now, this material will be more expensive, but way more, quality-wise higher than regular fiber reinforced composite. Now, where would you put that kind of high-performance materials? Well, in most responsible structures, which can also allow you a big expense to implement them. The known examples are again some kind of aerospace applications, biomedical applications. I am pretty sure that they are not used, to big extent in construction, because in construction you need, big volumes but low cost. So basically that's only the beginning of the process, but they can be used in many applications where the price is manageable and the quality is extremely important. You can make a little investigation on that. Any other questions?
Thank you. First, I'd like to know about those filament winding and those nano-composites, specifically when it comes to resisting compressive and traction loads. Are they best for one of them, or it depends more on how are they spatially organized?
Well, if you are talking about filament winding, right? Let's say you make a pressure vessel, right? So you want to have that pressure vessel which can sustain certain internal pressure, right? So what you can do, you can solve the optimization problem on how many layers of fiber and at which angles is best of all to put them. Well, it's not a big secret that probably you will come up with plus minus 45 degrees, then maybe 65 degrees, maybe 75 degrees. So how many layers? Again, there is a theory of laminates. These are cylindrical, but still laminates, because each time you have a layer of different orientation of fiber. So basically all that is within the what we call mechanics of composite materials. You can calculate that and you can make a design of that, and then you can implement that particular design on the machine that you saw. It is pretty much controlled. You can move that with certain speed, you can rotate it at certain speed, so you can basically make any angle whatever you wish. So basically that's the answer to your question, I believe. Yes, please.
Concerning that smart bridge in which you made
Yeah.
part of,
Yeah.
actually I'm curious about the type of smart materials you use for the monitoring.
Well, if you are talking about my personal experience, I can comment on that. In Canada, we had what was called, well, with unfortunate name, ISIS Canada, but that was before that ISIS happened. And this ISIS stayed for Intelligent Sensing for Innovative Structures. That was Network of Centers of Excellence. And I led a project on actually making glass fiber pultruded let's say cylinders, which are rebars that you put inside of concrete, with the fiber optic embedded inside, not simple fiber optic, but the one which has also fiber optic sensor. I showed you two examples, Fabry-Perot and brake grating. So that's what we did. And after we manufactured them, actually I have 2 patents on the technology in US, and then you can put them in these concrete bridges, and then the bridge deforms, and you monitor the signal which comes out of the sensors. So in fact, we really used these embedded fiber optic sensors in real bridges. So that network now is finished, but of course I think that hundreds of highly qualified personnel and publications and patents are released. So basically that's the technology. Now will that be really with fiber optic sensors or some other sensors is another question. But of course the technology is in place, and actually it is already in place in many places. Like for example, there is no airplane which does not have an overall sensing system in all parts of that plane, right? Well, the bridge is a little bigger, but they also have very well distributed sensors all over the critical places in the body. So basically it is already in place, and of course the future is more and more about that, definitely. And the beauty of that thing is with all this Wi-Fi, wireless connection, you really don't need to be there in that remote location with that bridge or with that, structure, or dam or whatever, overpass. You can be in the headquarters which monitors maybe hundreds of them at one time, right, at the real time. So is it reality? Well, not quite, but it's definitely where we are going.
I was wondering if we could use electric materials for monitoring, but I don't think the sign is too strong. I don't know.
Yeah, we thought about that, to use piezoelectric materials, but then we gave up it because piezoelectric material also needs some electric field and all this wiring, and it has some kind of hazards with electric implementation in remote locations of structures, while the fiber optics is 100% safe. The worst you can do is just break it, right? So, but you cannot damage the structure. So that's why fiber optic was considered to be. And also fiber optics is the way of communication, right? Gaining all these electric metal fibers are replaced more and more by fiber optics, right? Yes, please.
In Canada, you have a major problem of durability in the bridges because of the ice and salts.
Yeah,
in the
yeah.
winter. Do you have any sensor that you can monitor the degradation of the concrete?
Yeah, that was one of the main reasons. The problem is in rust. Because of this cycle of freezing, melting, salt, and also exposure to the oceans, if you like in place where I live, and many other places, the problem of corrosion is extremely important. So, parallel to idea of putting fiber optics was also the very winning idea of putting, instead of steel, or well, I say metal, right, the composite rebars. And this is done. I mean, composite rebars are already, very widely are used. Now, 2 types were investigated in time I worked there. One was with glass fiber reinforced, another was with carbon fiber reinforced. The glass was somewhat not as good because in high pH levels, apparently the glass fibers deteriorate as well. It doesn't rust, but then it has another kind of destructional problems. Carbon was much better, but the carbon was 10 times more expensive at that time. Now it's maybe difference not as big, but still it is quite considerable. So it was considered that making high volume carbon reinforced rebars is like by shooting with big gun to a fly. It was over designed idea. So basically the question is still open. The quality versus the price comes in place. Weight also can be reduced. Of course, with concrete structures, the rebars are not as important, but still, replacing very heavy metals with these FRPs is also gain in weight, right? So yeah, the progress is considerable in this direction. More and more critical concrete structures do come with not metal, but rather composite pre-stressing and reinforcing rebars. Now, I'm not a civil engineer, but I was collaborating with them. So basically, I know that the progress is very considerable there. Any other question? Well, thank you then very much. If you have questions in the future, you can always contact me. And of course, Professor Pacheco knows my coordinates. And you can find me easily if you put my name on Google. I think there are like a couple of dozens of pages, unfortunately. All right, guys. Thank you.